You can see the screen, all right? Okay.
Yeah, we do.
Great. So my name is Minah Young, and I am a postdoc at the Carr Institute in New York, and I'll be presenting the work that I did during my PhD at CU Boulder with my PhD advisor Ian Grooms and also Sophia Stanley. So we'll be talking about using generative models for machine learning for analog ensemble methods for data assimilation. Okay. So we're motivated by the fact that running an ensemble is expensive for very complex problems. And also we have at our hands many, many historical data sets or catalogs, and we should try to use them via machine learning. So today I'll introduce the different extensions of ensemble optimal interpolation, ENOI, that uses analogs. In particular, we're interested in constructing analogs with machine learning, and that is a method that's been introduced by Grooms last year, and we'll be improving this by adding a patching algorithm and also by generalizing the machine learning framework. And we show the results of doing that on a 1D toy model. And next, we also show some preliminary results of using this method in a 2D model that uses coupled data assimilation. Okay, so everything that I'll talk about today has to do with estimating the background error covariance matrix. So we have here our familiar common update formula and the common gain matrix, and all we're doing is figuring out how to best estimate the B matrix. So as we all know, in ENKF, we forecast an ensemble and compute the sample covariance matrix, which then approximates this B matrix. And in ensemble optimal interpolation, it's done in a different way. So this is the case in which we assume that we have some data set that describes the dynamics of the system that you're looking at. So this could be some historical data set, for example. And before starting a data assimilation, you simply sample a random number of model states from this library and compute the sample covariance matrix to approximate this B matrix just once. And so this gives us a time-independent covariance matrix because we don't ever change it once it's been formed in the beginning. And some benefits from doing that is that it's very cheap. Running this is very cheap because you only need to make a single forecast instead of, however many ensemble, the size of the ensemble number forecasts. And while this seems like kind of a rudimentary method for approximating the error covariance, it's shown to be appropriate for ocean dynamics and is used at NCAR for high resolution ocean models. So what we want to do is extend this idea of just approximating the sample covariance matrix by using analogs. And an analog is kind of a vocabulary from forecasting, where it simply refers to some state in the catalog that is close to the current model state. So what we want to do is we want to compute B by choosing analogs that are close to the current model state at each time of assimilation. And so this is now time dependent. So analog ENOI refers to at time of assimilation, going to your library or your catalog and choosing your NE nearest analogs. And there's a lot of ways to do that, like how do we define what's near and what's not. But the gist of the idea is you pick from the data set that you already have that's consistent with your system. Constructed analogs are different in that what we do instead is we use generative models for machine learning that have already learned from your library. So instead of going back to the library to pick the nearest analogs, at time of assimilation, you use your generative model to form analogs that are close to that current model state, and then use those generated analogs to approximate your background covariance matrix. So Grooms has explored the use of variational autoencoders to do so. And it's good that we kind of already got a really good introduction to what variational autoencoders are in the first talk. So that gives me a little bit less to do, I guess. Yeah, so, but let's just kind of review what they are. Autoencoders are a specific type of neural network that have two parts, encoders and decoders. And typically the encoders reduce the dimensionality in this nonlinear mapping. And the second half, the decoding, is kind of where the generative modeling part comes in. You can, you put in something in this latent space to output something that you're interested in. And this is an unsupervised method because our inputs we want our outputs to be the same as our inputs. And the emphasis here is in the generative modeling aspect of using autoencoders. And a variational autoencoder is a specific type of autoencoder. And as the first speaker mentioned, we have to enforce certain requirements for the latent space, mainly that it is from a standard normal distribution. And this is done by adding this Kullback-Leibler divergence term, which is a measure between two probabilistic distributions. And here I have it down as a standard normal distribution, but technically you can do it to whatever distribution that you want. But it's nice to be working with the standard normal distribution, so that's what we do. So yeah, a variational autoencoder is a specific type of autoencoder that has this extra condition that the latent space is encouraged to be a standard normal distribution. Next, I introduce to you the 1D toy model that we'll be showing most of our results on. This is a multi-scale modification to the Lorenz 96 model. It's multi-scale in that you can definitely see the small and the larger scale separation. So this is a 1D model, so the vertical axis shows the state and the horizontal axis is in time. So we're looking at the evolution of one instance of this model. It's initialized and a noise very close to 0. And the main thing to note from this figure is that in this zoomed in version of a quarter of the domain, you see two large waves fitting in there. So the scale separation between the large and the small scales are at about the 1/8 of the spatial domain. All right. Let's get to the method. We'll show how we use variational autoencoders as a generative model and how to extend that to just general autoencoders, not just variational autoencoders, and also introduce you to the patching algorithm so that we could potentially use this method for actual or more complex geophysical problems. So to do this method, you first have to train your variational autoencoder or general autoencoder with the catalog that you have. So that really means that from all the samples that you have from your historical data set, you set the input, those samples to be also the outputs, and you can choose whatever structure you want exactly to be the encoder and the decoder halves. But we will be working with using convolutional neural network for that, similarly to what the first speaker did. And so once you have trained and are satisfied with the VAE that you've trained, then at each time of assimilation, you encode your state variable. And to generate a new analog, you then add noise to this encoded state in the latent space, and then you decode that sum of the encoded state and the noise added to, and you decode it to generate a new analog. And when we're using a variational autoencoder, how to choose this noise is pretty straightforward because we have, ensured or at least encouraged the best we can for the latent space to be a standard normal distribution. So we can sample our noise from the standard normal distribution. There's this R sub Z parameter that, shows the amplitude of the noise. So that's a little bit of a tuning we have to do with this extra parameter. But the point is you can sample from the standard normal distribution when you're using a variational autoencoder. So that's how you generate one analog, and you can really generate as many analogs as you want by simply adding different noise. And by different, I just mean different samples from the standard normal distribution. And so as an example, you can create an any size ensemble by adding any distinct noise to the same encoded state in the lane space and then decoding that whole thing out. And then using these analogs to compute the sample covariance matrix. And we go on, put that in our data assimilation scheme, and yeah, that's how that works. And we can also do this with the general autoencoder, but the main challenge is in deciding what kind of noise to add to it, because now we have no idea about what the structure of the latent space is. So what we do is we do a simple affine transformation. So remember that in your training portion, you had used your historical data set to find this mapping from your data set to the latent space distribution. So what you do is you map your entire training set into the latent space and try to compute some statistics of that latent space. So you can easily figure out what the mean is and what the covariance is. So if the latent space of the encoded training set gives us or has a sample covariance matrix sigma, then we can compute its Cholesky factor so that we can generate noise that have the same covariance structure. So we're working with the Cholesky factor with the lower triangular decomposition in this case. But what you do is now when you're generating an analog, you would encode your state variable as you did before using your encoder. And then instead of just picking noise from the standard normal distribution, you would then transform that encoded state into this new space that has zero mean and identity matrix. Add noise from the standard normal distribution in that transformed space, and then transform back to your latent space, and then decode that sum back to your original space. And so, so that describes, this equation describes that procedure where this Z prime is the affine transformation of your encoded state into the space that has zero mean and identity. And if you, undo that transformation again, you end up with a much simpler formula where you still sample from the standard normal distribution, but then just apply the Cholesky factor in front of it to generate, a noise that has the same covariance structure as that latent space. So this is how you would generate analogs using a general autoencoder. And so obviously there are a few extra steps of doing this because you now need to compute the sample covariance matrix, you need to compute its Cholesky factorization, but there are also some benefits as well. Like now your autoencoder structure is simpler because you only need to be outputting just one vector in the latent space, whereas the VAE would require two vectors in the latent space. So at the end of the day, they turn out to be pretty similar in terms of how much it costs to apply this within data assimilation. But one definite benefit is that training a general autoencoder is faster because it has a simpler architecture. So those are kind of the different trade-offs between using a variational autoencoder versus a general autoencoder. Now we'll talk about the patching scheme. We're motivated by the fact that in real problems, all of our state variables are very large. So for example, a simple eddy resolving ocean model can have a sample that has up to like 4 gigabytes per a single 3D variable. So that means that a single model state would have something like 16 gigabytes just to identify what the sample looks like. So you could imagine if you're now trying to train a model that can describe this huge data, as in where a single sample is this large, then that also becomes, the problem becomes unfeasible at that point. And so the idea is to divide your state space, or your model state, into smaller digestible chunks. And then each chunk can go through an autoencoder structure. And so when you do this, you increase the number of your training samples, because what used to be just one sample is now more smaller samples. And each of these patches can be pushed through the same autoencoder in parallel. So that's also one of those things that machine learning is good for, right? They use GPUs. They're good at massively parallel jobs. So that's the idea behind using a patching scheme. And as an example, I show you the multiscale, one sample from the multiscale Lorenz 96 model. And we are trying to divide the sample into 4 patches. And the first one in the upper left is kind of the canonical example of how you can, divide a chunk or divide a state into 4 different chunks. And what the other 3 variants are showing is just simply moving the patch boundary so that we don't have the boundaries occurring at the same location in your spatial dimensions at all times. Because if you imagine that we divide always using just this first patching scheme, then we could have extra errors popping up at these 3 specific patch boundaries, which would then lead to an ununiform distribution of errors. And so we want to avoid that. And the way we do that is by using these distinct shifts. And yes, this works only because this problem is periodic, but that's the problem that we're starting out with. Here I show you what an example of an ensemble that is generated using our method. So what's happened is all four of these analogs are generated from the same state. They were partitioned differently. They have different patch boundaries, and each of these 16 patches were encoded using the same variational autoencoder, then added noise to, then decoded. And you can see that even though all of these are generated from a single state space or a single sample, but still are able to form analogs that look quite different. So that's good. We want some variation in our ensemble. Next, we see.
Yeah, Lucia, you shouldn't wait too long before concluding. You've got a couple of minutes maybe to do so.
Okay. This is just showing that the amplitude of the noise that's added in the latent space leads to different, or analogs that look much different than, like if you add a large noise, then your analog looks more different than if you're adding small noise. So that pretty much sums up the algorithm. What we do is we partition our sample into multiple patches, push each of those patches through our encoder, add noise to them, decode, and then undo the patching. And this algorithm is just here to show you that this double nested for loop can be computed in parallel. Each of these parts can be done on different processors. Yeah. Okay. So I am going to skip some of the details of this because I don't have too much time, but I've experimented with using different size patches for our patched constructing analog EnOI methods. So the patch sizes range from 1/32 of the domain to 1/4 of the domain. And what we see here is that if we ignore the red line, usually the larger patches still do better. Or I mean, no, the smaller patches do a really good job of learning the state space. But if it's too small, then you lose the complexity, and therefore it's at some point that advantage goes away. And what we've seen is that when we train our VAEs on these different size patches, the large scale motions are always learned first. And it's a little bit more difficult to learn the small scale dynamics, but most of the energy is contained in the large scale. So that could be considered to be okay. And when we take a look at how our different, our VAEs trained on the different patch sizes do in data assimilation, let me skip this slide. We see that there is a relationship between the quality of your variational autoencoder strictly in the machine learning metric of the reconstruction error, which is how close is the output to your input. And that has a positive correlation with how well does our VAE do when measuring the data assimilation RMSE when using them as a way to generate analogs to estimate our background covariance matrix. So we see this nice trend here of when we have a smaller reconstruction error, our data assimilation root mean squared error is also small. We see that the red line here shows that because the 1/32nd patch VAE isn't able to get a good reconstruction error, it doesn't improve after this point. It also doesn't improve the data assimilation results. And what's really interesting is that even though the quarter patch, which is the largest patch that I used, has a larger reconstruction error than the 8th patch and the 16th patch sized VAEs, it still gets a very good or the best data assimilation RMSE. So it seems that there is some more work to be done about how to choose what kind of patch sizes you could be using. And I guess I don't have too much time, so maybe I'll just skip this.
You don't have any time left, unfortunately. So, I mean, it's better maybe if you take a few questions. And there is already a couple of questions for your talk.
Okay, sure.
So maybe you want, go ahead. Say take 30 seconds to conclude, and then we move to the question.
Sure. Okay, so I've introduced to you a way of using machine learning as a generative model to construct analogs to estimate the background covariance matrix, and some ways of improving this method by allowing to use general autoencoders instead of VAEs, and also using patching to make this more feasible for bigger problems. Too many / too small patches lose the advantage, but so there's a little bit of work to do about that. But overall, it seems promising, and we are developing how to do this for coupled systems, and some other future work include trying to coming up with a solution for non-periodic domains. Okay, thank you.
Okay, thank you very much, Lucia, for this very clear talk. And so we have, maybe 3 questions, but I'll take 2. So there is one from Irsto Shipilski. So have you tried using other generative models to construct your analog ensembles, for instance, generative adversarial networks or normalizing flows? If not, what was your motivation for choosing VAEs for this problem?
Okay, so we haven't used GANs for this. It's a little bit trickier to do GANs, and our motivations for using or staying with the autoencoder structure was simply that there's a really clear way to generate analogs, like the method I described by adding noise in the latent space, whereas the equivalent of that for GANs is a little bit more unclear for us, so that's why.
Okay. And there is another one from Daisuke Ota. So he has a second one, so I'll let you answer in the chat. But so let's take the first one. So in patching scheme, how do you ensure spatial consistency across adjacent patches?
So we don't here, but so in the future work, that's something we could do to try to smooth out these stencils, but we do shift the patch boundaries to at least make the errors uniform. Yeah.
Was there any overlap between your patches?
No.
No, you didn't. Okay. So that's something to try.
Sure.
Okay. Thank you very much, Lucia. We need to move on.